In this next section, 6.4, we're going to look at conservation of energy in a closed system. And in particular, we want to look at how kinetic and potential energy can interchange with one another. Now, when we say conservation of energy, energy is always conserved, but it can go into the form of heat where we can't really get it back in a useful way. And so we often say energy is conserved when none of it goes to heat, meaning actually what? That the useful form of energy is conserved. And the unuseful part, heat, goes off, in some other useless way that we can barely get any of it back again. Okay, how would we look at this, say, with the gravitational field? Well, this is a very standard kind of problem. If we look at a cliff or a building, and the building has a certain height, we have a mass up here on the top of this building, a mass m, and let's say it falls off given no initial velocity. Then what happens is we originally had some potential energy, and we're going to trade that off for kinetic energy. What is it? Well, the potential energy is going to be equal to m times g times h. The mass that we have times g, which is 10, times the height. That'll give us our potential energy. Well, what's going to happen to that energy? As the object heads down the side of the building, it's going to go faster and faster. At every point, it's losing height, so it's losing potential energy for gravity, but it's gaining kinetic energy, so it's going faster and faster. So we can say that the kinetic energy, which is equal to 1/2 mv squared, plus the potential energy is going to be constant. So we can say kinetic at the top of the motion, height originally or initially with an initial velocity, is going to be equal to 1/2 mv final squared at the bottom plus mgh final. Well, there's a very fast way to solve this. We can say the position down here is x equal to 0. So it has no height when it gets to the bottom. And at the top, we give it a slight tug off the edge, but it really has no initial velocity. So this vanishes. This tells us that 1/2 mv squared at the bottom, the kinetic energy, was the potential energy at the top. And notice here that the velocity of the object is going to be independent, as Galileo discovered, of what the mass is that we dropped. Therefore, we can calculate the velocity at the bottom as the square root of 2gh. This is a very useful formula. You can work hard to try to get that with our previous equations used in mechanics, but to find the velocity of something that's dropped is very easy here using conservation of energy. You simply write the kinetic equal to the potential and solve for the velocity. So, for example, if we had, well, let's take something like a building, and let's now use, for a change, let's use feet. Let's take an 8-story building, and let's assume that we have about 12 feet in each story, and that would be 12 times 8, 8 and 8, 16, 8 was 96. So let's say about 96 feet high. And what is g? Well, you recall g is 32 feet per second. So our velocity at the bottom is going to be the square root of 2 times g, which is 32, times h, which is 96. Now, if you look at this, we have 3 times 32 would give 96, so this was actually equal to the square root of 2 times 30. Well, we can take our 2 times our 32, which would be 64, and write this 96 as 64. Let's see. Oh, that's not a good way to do it. Let's try a different way. Let's look at our 2, our 32, This is 3 times 32, which is 96. So this is going to be, we can have a 32 squared, which we can bring out, 32 times the square root of 6. And that's going to give us our velocity in feet per second. Well, the square root of 6 is going to be roughly, the square root of 4 would be 2, 9 would be 3, so there'd be 2.5. So 2.5 of these would be 64 plus another half, which would be about 16, 70, 80. Turns out that this is very close to being 88 feet per second. It turns out that 88 feet per second is the same as 60 miles an hour. So roughly speaking, if I jump off or push something off of a 8-story building, and these 8 stories have about 12 feet apiece, then very roughly, the velocity at the bottom is going to be 80 feet per second. And that 88 feet per second is going to be 60 miles an hour. So in round terms, you can say you're going to be going about 60 miles an hour if you were to jump off that building or if you're going to drop something. It was very interesting to compare that with a car. We don't think anything about passing a concrete abutment at 60 miles an hour. Yet that would be the same as hitting that abutment as driving off the top of an 8-story building in our car. And you can imagine how frightening that would be. So anyway, this gives us a way to calculate the velocity at the bottom using conservation of energy. We're now going to do that using a spring. We can easily imagine that we slide down somewhere, convert something into, from potential energy up here to kinetic energy here, and then we have a spring, and the spring gets compressed back to some distance here, distance x, and as that spring is compressed, this mass moves back here, and then finally it stops. The spring will then decompress and throw it in the other direction, and it would throw it all the way back up the hill to its original point, assuming we didn't have any loss of friction. Well, one thing to think about for that's very common is to think of exercises with these spring devices. You see these on TV all the time where you have something where you have a spring, you put your hands on these 2 springs, you stretch them out. There's the poor guy doing this. Stretching these out, and of course every time you do that, it's relatively easy to cheat, it turns out. Why is that? Well, a spring has an energy associated with it, a potential energy. Potential energy of the spring is equal to 1/2 kx squared. Well, you notice this goes as the square. Therefore, somebody who pulls twice as far does 4 times the work. So if you just pull this thing slightly, you're doing almost no work at all. And so it's easy to say, I did so many repetitions with the spring device, when in fact, each one of those reps through a small distance gave you almost no potential energy and therefore almost no work that was done. But again, if we look at springs and as they oscillate, we can have a spring, and as it oscillates back and forth, we get to a high compression or high expansion rate. If this is the distance x, it would be 1/2 kx squared. In the middle, that's converted to energy. So we can say 1/2 mv squared plus 1/2 kx squared is equal to a constant. That's the constant amount of energy that you have. And you can start out by pulling the spring out right here, or you could give it in the middle and give it a boost, and it would travel at a certain speed. So you can see here that it's very easy to calculate back and forth between the kinetic energy and the potential energy. You could write this constant energy and saying this was initially, and the final is 1/2 mv final squared plus 1/2 k x final squared. And if I compare two situations, like an extreme position with a position of 0, where I have extreme velocity, then we could say initially I'm out here, so there's no velocity, and I've got 1/2 kx squared. And at the center, I can compare that and say I've got 1/2 mv squared, and the position is 0. Position 0, velocity 0. And now you can see the 1/2 cancels the 1/2, and I get k times x squared is equal to m times v squared. And so we're able to relate the maximum position to the maximum velocity, or the kinetic to the potential energy, either way, by using that conservation of energy equation.